forward. Okay. All right. Well, I'm excited to introduce to you today Professor Dan Wasserman. Before handing it over to him, let me tell you a little bit about Dan. So Dan received a bachelor in engineering, physics, and history from Brown University. Then he attended Princeton University, where he received both a master and a PhD in electrical engineering. And after his PhD, he stayed at Princeton as a postdoctoral fellow and worked in Claire Gmachel's group on quantum cascade lasers. I think that's about the time when we first met, right? At these awesome small QCL conferences. Those are always fun.
That's right.
And then in 2007, Dan joined the Department of Physics and Applied Physics at the University of Massachusetts Lowell, then switched over to the Electrical and Computer Engineering Department at Illinois Urbana-Champaign, and now he's at the University of Texas at Austin. So he went through all of the cold the last few weeks ago. And I'm glad to hear that you're back to having water. He has received many awards, such as the NSF Career Award, the AFOSR Young Investigator Award, the UIUC Distinguished Promotion Award, multiple teaching and advising awards. And in 2018, he was also elected a fellow of the Optical Society of America. His research is focused on mainly, I think, mid-IR and far-IR emitters, detectors, and photonic devices for a wide range of applications in defense and security, sensing and communications. And today he will talk to us about all-epitaxial mid-IR plasmonic optoelectronics. And with that, I will give it to you. Excited to hear about your work. It's always fun.
Thank you so much, Inez, and thank you so much for inviting me. It's a real pleasure to be there virtually, I suppose. Inez has promised to invite me back in person at some point, so I'm excited for that as well. So today I want to talk to you about my group's work in all-epitaxial plasmonic optoelectronics. And before I do that, I would like to introduce the people who actually do the work, and that is my students and postdocs. So this is my my team. And in addition to my research group, of course, a lot of this work was done with a number of collaborators, in particular, Victor Podolsky at UMass Lowell and Seth Bank at UT Austin, as well as a number of other friends and collaborators. And of course, the people who actually pay for the work. A lot of the work that I'll be presenting today is funded or has been funded by NSF, but also AFRL, Sandia, Lockheed Martin, and DOE. So in sort of broad strokes, I lead the mid-IR photonics group at UT Austin, and sort of in the broadest strokes, our group designs, grows, fabricates, and characterizes materials and devices for the generation, detection, and/or manipulation of IR light. And if I had to sort of boil even that down into a sort of smaller mission statement, it would be that we're trying to do nanophotonics with micron scale photons. So what I'm showing here is a picture of our campus. This is the football stadium. And if you're not familiar with the University of Texas, we are actually a football team that got accredited as a university, I think, along the way. But this is our new building. They actually built a building that was a non-football related building, as far as I know. So this is our Department of Electrical and Computer Engineering building. It's called the EER building. It's brand new. I haven't been in it in a year, but I'm looking forward at some point to getting back to it. So I want to give an outline of how I'm going to lay out this talk. The first, I'll of course give an introduction. I want to talk a little bit about, what is the mid-infrared and why we might care about it, and what are the challenges of working in the mid-infrared, and then how we design optoelectronic devices for the mid-IR, really for any wavelength range. And I'll talk about how we actually engineer materials to make these optoelectronic devices, and how we can control our optical properties, but also our electronic properties and our device architectures, and then how we can put all of that together into sort of monolithic optoelectronic devices for the mid-infrared. So what is the mid-infrared? And the mid-infrared sits somewhere between sort of the shortwave infrared or the near IR, which we generally associate with telecom, or even sort of a little shorter wavelength, the visible, which of course dominated by consumer electronics properties. It sits in between this very, very well developed optical frequency range and the longer wavelength terahertz or even sub-millimeter microwave wavelengths, right? So the mid-infrared sort of sits in this range, let's say, of about 2 micron wavelengths out to 20, 30 microns or so. And of course, it depends if you're talking to someone in the defense, they have a very different idea of what the infrared is. If you talk to an astronomer, they're completely different idea of what the IR is. But so for the purposes of today's discussion, I'm going to say between 20 and between 2 microns and 20 microns, right? So why do we care about this wavelength range? I typically give sort of two very glib answers. And the first is that everything absorbs in this wavelength range. So a wide range of molecules have fundamental vibrational, rotational resonances in this wavelength range. So it's an important wavelength range if you want to do optical sensing for breath analysis, for environmental monitoring, for industrial process monitoring. And so this is simply a plot with shows a number of sort of important molecules that and their absorption or their position of their absorption resonances within the mid-infrared. And you can see here the absorption spectra for ammonia, which shows the sort of discrete and distinct absorption lines. We often call this a molecular fingerprint. And you'll see that the strongest and sort of densest array of the sort of fingerprint occurs in the mid-infrared in sort of the 8 to 12 micron range, which is often called the molecular fingerprint regime of the mid-IR. But if everything absorbs in the mid-infrared, then it turns out that actually everything also emits in the mid-infrared. And that means not just jet engines and helicopters, but graduate students and other forms of life, or even electronics, right? So if you want to track something, you don't have the advantage of ambient light, an infrared sensor can allow you to track heat signatures. I just to be clear, I don't track my graduate students using heat signatures, though I suppose one could. And I guess one more reason is the mid-infrared is, of course, a very long wavelength range. It's still in the optical frequencies, but these long wavelengths means it's difficult to scatter mid-infrared light, right? So small particles won't be seen essentially by this long wavelength signal. And so you can see that you have these two transmission bands in the atmosphere, what we often refer to as the mid-wave infrared between 3 and 5 microns, and the long-wave infrared between approximately 8 and 13 microns. So there is some interest in free space communication using the mid-infrared. It might be good in an environment where you have a lot of dust that might scatter shorter wavelengths, but not longer wavelengths, or for remote sensing applications. So that being said, it's an important wavelength range for these sorts of applications, but it's also a very challenging wavelength range to work in. And the challenges are actually very much related to the reasons why the mid-infrared is such an important wavelength range. Namely, everything emits in the mid-infrared. So if you want to make a source, it has to emit above the background of everything else in the world that is emitting, essentially. And if you want to make a detector, you have to be able to differentiate between the sort of background signal and the actual signal that you want to detect. And the fact that the semiconductors that we use for mid-infrared tend to be these narrow band gap semiconductors, the thermal energy just inherent in the actual devices can cause all sorts of problems. And just like everything emits in the mid-infrared, everything absorbs in the mid-infrared, and a lot of materials absorb very well in the infrared. I'm showing here a visible picture of somebody holding a pane of glass in front of them, and of course, superimposed on that is the thermal image of that same thing, and you can see that the glass, of course, is opaque in the mid-IR, and you might not think that's a big deal, but of course, glass is the backbone of our communication infrastructure because it is transparent, it is low loss, and it's very cheap. And so not having a material like that in the mid-infrared can make things very difficult. So it's not always easy to find good, cheap materials in the IR. And a lot of the material properties that we're familiar with from visible or near IR materials, they can be very different in the mid-IR. The mid-IR materials can behave very, very differently than the same materials at shorter wavelengths. And then tied into this, the advantage associated with the long wavelength of the mid-infrared is the challenge, right? Which is that your diffraction limit, of course, scales as wavelength. And so even though you have less scattering, it's really difficult to make an argument that the mid-infrared is a good place for nanophotonic applications because your wavelength is just longer. So all the sort of ideas associated with optical interconnects and quantum computing or computation, nanosensing, you want nano emitters and nano detectors and nano waveguides, but you just increase the wavelength of your light by a factor of 10, which makes it that much harder to get to the nano. And then finally, the last but not least reason why working in the mid-infrared is difficult, this is important for any PI who's trying to run a lab, is money. So you want to buy a polarizer in the visible, that might cost you $80, but a polarizer in the mid-infrared is going to cost you more than 10 times that. Same thing goes for sources. You want to buy laser diode in the, and I'm just using, these are prices from Thor Labs from some time ago, but the same trend holds today. A near IR laser diode might be 10, 20, you can buy a laser pointer, of course, for next to nothing. But if you want to buy a quantum cascade laser, it's going to be $5,000 on Thor Labs. And to be clear, the fact that you can buy a quantum cascade laser on Thor Labs is amazing. I don't know that I ever thought that would have happened when I started my PhD, but nonetheless, it's still order of magnitude more expensive. So when we think about designing an optoelectronic device, what do we essentially need? Well, we need optical access, right? So we have to bring the light into our device, or we have to get the light out of our device. We of course have to either generate the light that's then leaves the device, or we have to absorb the light that's coming into the device, right? And we need electrical access, because what we're talking about here are devices, not just structures. So we need to be able to drive the device to generate an optical signal, or we need to be able to convert an optical signal into electrical signal and extract that signal from our device. If you think about how we design optoelectronic devices, these are the three basic components that we need to be able to work with, right? And the question is, can we do all of this and still go nano and work in the mid-infrared, right? So that's sort of the challenge, the bigger picture that my group is trying to address. So if we think about how we design materials for optoelectronic applications, at the most fundamental level, of course, what we're trying to do is get light to interact with matter, right? And we know that light is an electromagnetic wave, and that means it consists of electric fields and magnetic fields. And so when light interacts with matter, its electric field is essentially interacting with charge, and its magnetic field is effectively interacting with current. We can think of different charges and currents that the electromagnetic wave can interact with, and we can break that down into the idea of bound charge, which basically gives us our dielectric constant or refractive index. We can think of free electrons, right, that can give us a plasma response. We can have light interact with phonons, lattice vibrations in our materials. We can engineer optical transitions in our materials, or of course we can have light interact with magnetic resonances. Now, I'm mostly interested in engineering the electrical response of our material. So that means I'm engineering the permittivity of a material. So in the mid-infrared, one of the reasons why it's such an exciting place to work is because we have all of these different light matter interactions that we can play with. And I'm going to talk about a number of them in the coming slides, right? So we have free carriers, and we can design structures that interact strongly with free carriers. We can design or engineer plasmonic materials. So not just, perfect electrical conductor type metals, but plasmonic materials. We of course have a number of dielectrics. We have optical transitions. We have lattice vibrations in the mid-infrared, and we can even see nonlinear effects. But the real reason why the mid-IR is so exciting is not simply that we have these light matter interactions, is that we have mechanisms by which we can engineer each and every one of these light matter interactions. And that's what makes the mid-infrared such an exciting sort of playground to work with if you're trying to design optoelectronic devices. So how do we go about designing our optical materials? So our ability to design optical structures, right, what we really want to do is control light matter interaction, requires the ability to engineer of course, not just the geometry of our structures, but also the permittivity, the way that our materials respond to electric fields, right? So if we wanted a full optical toolkit to engineer materials, we would want to be able to have metals, right? So that means plasmonic response and epsilon near zero response, and ideally perfect electrical conducting materials. We'd want dielectrics and the ability to control the refractive index. And then some combination of those, some structured subwavelength combination might give us things like metamaterials, right? And we want to design these all to integrate with quantum engineered active regions. That's going to be our light sources or our light detectors, and electronic device architectures that are going to allow us to bring the electrical signal into or out of our optoelectronic device, right? Now, doing this on any length scale is a challenge, but it becomes particularly difficult at the nanoscale. If we can do this all in a single material system, then we gain a real edge towards being able to make nano optoelectronic devices for the mid-infrared. And ideally, we want to do this in an epitaxial system that's going to give us the highest quality material and the most control over these different parameters. So how do we go about engineering an optoelectronic device? Well, I'm first going to talk about how we engineer the material properties of our devices. So of course we can use traditional metals, right? So metals have somewhat unique properties, right? They can be highly reflective. In the shorter wavelength range, they can behave as plasmonic materials, but we can use metals, for instance, to support surface waves. So this is work that I did with my colleague Victor Podolsky, where we showed that we could essentially use a corrugated surface to effectively focus or steer scattered light from surface waves. We can design essentially IR antennas, which in this case we use to engineer selective absorption and then selective thermal emission. So we could engineer surfaces that would emit at certain wavelengths in the infrared. Or we can, of course, use dielectric structures. So this is a guided mode resonance filter that we designed. It consists of a silicon nitride on a calcium fluoride substrate with a periodic square lattice that we patterned into the silicon nitride. And we can couple into these guided modes via the pattern surface. And we can get these really, really strong, narrow filtering modes, right? But the thing that sort of ties all of this together is that all of these structures are diffraction limited, namely that this is essentially just a dielectric waveguide, and on the metal surface, we are dealing with wavelength scale structures, right? It's because we're using off-the-shelf materials and we have no control over the permittivity of our materials, right? This requires polylithic integration, namely we have to slap a bunch of different disparate materials together, right? And these are all diffraction limited, right? If we want to beat the diffraction limit, we need to figure out a way to get small mode volumes. And the way that we do this in optics is with plasmonics, right? Now, plasmonics, of course, is the essentially the field that studies the modes that exist at the interface between a metal and a dielectric, right? So if we look, we can sort of divide this into two types of plasmonic modes: the surface plasmon polariton. This is a guided mode that propagates at the interface between a metal and a dielectric, and the localized surface plasmon, which is, as its name suggests, a localized mode that sits on a subwavelength 3D particle, metallic particle surrounded by a dielectric environment, right? And if we look first at the permittivity of a typical noble metal, one of the things that we notice is that in the mid-infrared, our metal is essentially a perfect electrical conductor. So the permittivity is remarkably large and negative. So it behaves like a perfect electrical conductor. It's highly reflective. And if we look at the expression for our surface plasmon polariton wave vector, we see that in this regime, basically what you have is you just have a guided mode that's basically has the wavelength of light in free space. So it's guided in the sense that it is a surface mode, but it's not tightly bound to that surface, right? Because the permittivity is so large and negative. Now, if we look at the visible wavelength range, in this range, we can actually see what we call a plasmonic response. And the reason why we can have this plasmonic response is because we can get sub-wavelength confinement of our modes, because our metal dielectric is negative, but not so negative that it looks like a perfect electrical conductor. And we can continue going to shorter wavelengths and not, we can get to the point where our permittivity is effectively zero or near zero. This is called epsilon near zero, or ENZ. And there's a lot of interesting things that happen optically at ENZ, because as you can imagine, when your permittivity goes to zero, your refractive index goes to zero, your wavelength becomes infinite essentially, right? So there's some really interesting work being done right now in epsilon near zero materials. But what this effectively means is that if you're trying to generate or trying to support a plasmonic mode, for instance, on a propagating wave on a metal dielectric interface, what happens is that they can propagate for a long distance. And the reason they can propagate for a long distance is that they're not tightly bound. So this is the penetration depth into the dielectric. And you can see that the penetration depth of the surface mode is on the order of between 1 and 10 wavelengths. So this is not a subwavelength mode. You're never going to be able to go nano with a traditional metal dielectric interface in the mid-infrared. Right? So you have long propagation lengths, but that's because you're not really interacting with the metal. You're not tightly bound to that metal. If you look at the localized surface plasma, and this is the response for the polarization of your plasmonic particle, you can see that the denominator here, right, will go to zero when your permittivity of your metal is negative and approximately equal to 2 times the dielectric, the surrounding dielectric permittivity, right? But if your metal permittivity is negative 10,000, that's not going to happen, right? So you can't actually support these modes on a noble metal particle in the long wavelengths where you have these large negative permittivities. So all of the cool stuff that we want to do with plasmonics in the mid-infrared, actually you cannot do this with traditional metals. But we can think about how we might engineer metals, right? If we go back and think about from a fundamental point of view, how metals respond to incident light, we can treat the metal essentially as a dielectric with bound charge, some background permittivity, and a bunch of free charges that are sloshing around, right? And then we can simply apply Newton's law, right? Newton's equation of motion with the damping term, and we can go through and solve that. And what we end up with is an expression for the displacement of your electrons, and then a polarization and an effective susceptibility, which we can convert into a permittivity. And what we see, this is nothing more than the Drude model for free carriers in a material. What we see is a permittivity that at frequencies close to this plasma frequency, so when omega is approximately equal to omega p, you end up with a permittivity that is basically zero. And as omega gets smaller, that permittivity becomes negative, right? So we can actually find a material system where if we can control the amount of free carriers we put in that material system, we can essentially control the permittivity, and we can make our own metals. And of course, the material system is semiconductors, because we know that we can dope semiconductors to have a certain amount of free carriers. I mean, that's what semiconductor doping is. In fact, we can control whether those carriers are electrons or holes, and we can control the density of our dopants, right? And which gives us controls the density of our free carriers. And so we can actually tune the plasma frequency by changing the doping, and we can combine if we have our narrow bandgap semiconductors, which have both can have high doping and small effective mass. That means we can actually push the plasma frequency into the mid-infrared. Well, this leads us to a class of materials of epitaxially grown 3-5 semiconductors, particularly narrow bandgap semiconductors such as indium arsenide or indium antimonide. So this is not the best sample we've ever grown. This is in fact one of the very first samples we've ever grown. You can see 009. So that's in one of our first 10 samples that we grew at Illinois, where we just doped the heck out of a layer of indium arsenide on top of an undoped layer. And what you can see if you look at the reflection is you see these oscillations, right? Those oscillations are the Fabry-Perot oscillations in this doped indium arsenide at the interface here between this undoped barrier. And then at a certain wavelength, you see the reflection basically jump up to be close to unity. And so this is where your semiconductor is essentially transitioning from a dielectric to a metal. This is the plasma frequency of the semiconductor, and you'll notice that it's sitting here in the mid-infrared. So this is one of the very first samples that we ever grew, and you can fit this using the Drude model that we just described in the previous slide. So you can assign a plasma wavelength or a plasma frequency and a scattering rate. That's a damping term. And you can see that you actually get a remarkably good fit when you model your indium arsenide material simply as a Drude metal with some background permittivity, and then just using like a transfer matrix method to calculate the reflection and transmission. So what does this mean? Well, it means that we can epitaxially grow metals with properties across the mid-infrared that give us all the sort of things that we want to be able to do. Namely, we can have, if we sort of lightly dope, we can tune the refractive index without turning it into a metal. We still have a positive permittivity. We can cross over from positive to negative permittivity, and this would be our epsilon near zero. And then we have this range here where we have permittivity that is on the order of what the surrounding dielectrics would be, where we can exhibit plasmonic response. So we can make, for instance, nano antennas now, right? So I said we wanted to take micron scale wavelengths nano. We can generate these localized surface plasmon resonances, and you can see they're rather significant resonances that we're observing here. Distinct features associated with sub-wavelength plasmonic particles fabricated from doped semiconductors operating in the mid-infrared. We can also use these materials as epsilon near zero materials. So it turns out that if you can fill a gap in a sub-wavelength slit with epsilon near zero material, you can actually strongly enhance the transmission through this sub-wavelength gap. So this is the peak associated with the ENZ transmission through a sub-wavelength gap. This is experimental data, and basically what we showed is that you can beat the transmission through an undoped high index material using this, realistically rather lossy, but epsilon near zero material in a sub-wavelength slit. So we sort of showed, I guess there's one more thing that I want to mention, is that by, with this ability to control permittivity, we can now start thinking about incorporating regions of semiconductors that have negative permittivity with regions of semiconductors that might have positive permittivity. And this led to work done by my colleague Anthony Hoffman when he was a PhD student at Princeton, where he demonstrated that you could make what's called a hyperbolic metamaterial using alternating layers of highly doped and undoped semiconductor materials. And so this allowed for effects such as negative refraction and this highly anisotropic response in a layered metamaterial structure. So we now basically have a material system where we can have metals that not just sort of large negative permittivity, but plasmonic materials in the mid-infrared or epsilon near zero response. We can control the dielectric constant using doping. We can even make metamaterials, right? So with our doped semiconductors, we can do all of these things. So how then, if we sort of continue along this path, are we going to engineer our optoelectronic devices? Well, if we think about what we want to do, we need to be able to engineer optical transitions in the mid-infrared wavelength range. And of course, engineering optical transitions, if you think about it, is the basis of modern optoelectronics, right? So if all of the sources and detectors that we use for communication infrastructure, these are all made by being able to control optical transitions in semiconductor-based devices, right? So we can choose semiconductor for their band gaps, for instance. So this is, perhaps the simplest semiconductor device. It's a p-n junction. In this case, it has a quantum well in here. And of course, by controlling the material of your quantum well or by the size of your quantum well, you can effectively control the energy at which light might be emitted, right, from this quantum well. But of course, in the mid-infrared, we have a number of other really cool tools that we can play with. We have the quantum cascade laser, right? So these are complex heterostructures, and this is just the conduction band of a complex heterostructure. And you can see that essentially you're doing is you're quantum engineering electron wave functions, and you're designing a structure where you're controlling transport and the optical transitions of an electron. And then there's the close relative of the quantum cascade laser, which is the inner band cascade laser, which is slightly more complicated in terms of band structure, but ultimately it's the same basic idea that you're controlling transport and transitions between states in your complex heterostructure. So we have a lot of ways that we can actually control optical transitions in the mid-infrared. So if we look at PN junctions, this is work done with my colleague Larry Lee, who's now at the University of Illinois, where we showed that you could grow indium arsenide quantum wells on a indium phosphide substrate using a metamorphic buffer layer. And we fabricated lasers out of these devices that lays out to room temperature. But ultimately, these are limited by the band gap of your indium arsenide. So the indium arsenide band gap is around 3.5 microns. So you could perhaps move to indium antimonide, or INSBE, which has a band gap at 7.3. But INSBE's lattice constant's way out there, so you can't grow it on any real substrate. So that becomes a real problem, and there's no good band offsets to use with it. So INSBE is not a great material, and even if you could grow INSBE structures, it still only gets you out to 7.3. So as much as we would like to be able to make a simple PN junction with a quantum well in it, we're not going to hit the long wavelength infrared, the 8 to 12 micron range, with these types of devices. But what we can start thinking about is what's called type 2 materials. So type 2 materials are a little bit different. They have a band alignment where the valence band of material 1 sits above the conduction band of material 2, which means that you can make a quantum heterostructure here where your holes are confined in material A and your electrons are in material B. And what you essentially have is this diagonal transition between B and A. And by tuning this geometry, you can effectively tune the position of the valence band state right here. I hope people can see my pointer, by the way. I've been assuming that people, okay, good. And so you can control this this structure either by controlling the material system, or by controlling the alloy content, or by controlling the geometry. So this is what's known as a broken band alignment. Sometimes you'll hear people refer to it as a type 3 offset. And you have, in this case, electrons from the indium arsenide conduction band recombining with holes in a InGaAsP layer. So here you're not limited by band gap, right? So you have two different materials. Both of their band gaps are larger than the optical transition energy, but it's a fairly straightforward structure to grow, at least compared to some more complicated ternary or quaternary alloy materials. So we demonstrated that you could actually, because the lattice mismatch in this case between indium gallium antimonide and indium arsenide is basically the same as the lattice mismatch between indium arsenide and gallium arsenide, which gives you quantum dots, that you can actually form these type 2 quantum dots on indium arsenide substrates. And so we showed that you could get this nice quantum dot formation, and you could get very nice mid-infrared emission. And actually the mid-IR emission is pretty temperature stable. I mean, you lose about a factor of 4 when you go from low temperature to room temperature, but all things considered, for a semiconductor emitter in the mid-IR, that's really not so bad, right? So we can use these type 2 quantum dots, for instance, for mid-IR sources, but we can also make superlattices. So we can stack together these type 2 materials, so hundreds of layers of these, and instead of forming discrete states, what we get are mini bands. It's a superlattice. We're essentially forming a semiconductor on top of another semiconductor band structure, or two other semiconductor band structures, right? And by controlling the geometry and the materials, you can essentially control the energy spacing between your electron and your hole mini bands. What this means is that by designing different combinations of materials, or thicknesses of materials, we can actually cover everything from 5 out to 9, or even out to 15 microns now, if we want to, and essentially build our own semiconductors, quantum engineer our own semiconductors for operation in the mid-infrared and across the mid-infrared. Right, and we can make these into devices, of course, because these are all epitaxial systems, right? So these are LEDs that we grew with these type 2 quantum dots, and we can engineer device architectures for detectors. So we could do, for instance, a PIN detector, or just an N-type and P-type semiconductor with an intrinsic region. So this is a typical photo detector, but we can also do some novel photodetector designs like these baryode devices, where this is called an NBN for N-type barrier, N-type detector, where you absorb light in this N-type region, and then it's the hole that is transported. This barrier prevents a dark current from flowing. So these are low dark current, low noise devices, and you can even do something a little bit more complicated called a CBIRD, which is a complementary barrier infrared detector. So we have a lot of flexibility in terms of the types of devices that we want to design. So in addition now to having a material toolkit, we have a device toolkit where we can actually engineer active regions and we can engineer electronic device architectures. And not only can we do all this, but we can do this on the nanoscale, right? Because we're all of these devices that I've shown you and all these materials that I've shown you are all grown epitaxially. And I never said it explicitly, but you may have noticed that it's actually all in the same material family. All of these materials and devices are grown in the so-called 6-1 material family, namely the 6.1 angstrom lattice constant, which is basically gallium antimonide, indium arsenide, and their alloys, right? So that means that we have this sort of material system where we can engineer the optical properties of our materials, but also the electronic properties of our materials. And this is exactly what we wanted to be able to make optoelectronic devices for the mid-infrared. Okay, so let's think about how we might be able to put this all together. And let's start with the simplest case. So let's just take one of our quantum engineered superlattices, and let's put that on top of one of our doped semiconductors. Okay, so we have essentially a plasmonic ground plane, and on top of that plasmonic ground plane, we put an emitter. And so in this case, so what I'm showing here in the upper left-hand corner is the reflection from these devices. So what we have is we have an N++, this is our heavily doped plasmonic ground plane. And then above that, we grow a thin superlattice designed for a band edge of approximately 10 microns, 9.5, 10 microns. And we grow a control sample that is the exact same structure, but with an undoped ground plane. Right, so this is just a dielectric. It's not a plasmonic material. So if we look at the reflection, what we see is from the undoped sample, we basically just see a flat reflection, which is what you'd expect because the refractive index for undoped material is basically 3.5. And so you're basically looking at reflection from a dielectric surface, a high index dielectric surface. You would expect about 30% reflection. And our simulations bear that up. The simulations are here in the dashed. But if we look at our plasmonic system, what you see is this rather strong feature here at about 8.5 microns. And this corresponds to essentially a cavity mode that's set up in your system because you have effectively a plasmonic, a reflecting layer, and then a thin dielectric layer on top of that. And so what you get is essentially a thin film interference effect or a leaky cavity. Now, if we go and we look at the photoluminescence, namely we optically pump our thin emitter layers, and we look at the photoluminescence, the light that comes from recombination of our pumped electron hole pairs, what we see is a dramatic difference between our control sample and our sample grown on the plasmonic layer. In fact, what you see is about a factor of 7 improvement in your emission efficiency. And you also see your emission pulled a little bit compared to the control. And that's because this cavity is effectively pulling the emission, right? So what we're seeing here is a combination of a number of effects, and we go into this a little bit more in the paper, but basically you have a cavity mode, but combined with that, what you have is a Purcell enhancement. Purcell enhancement is when you have a very large photonic density of states into which you can emit. So you have these plasmonic modes that sit at the interface between your metal and your dielectric, and these are high density of photonic states. So your light wants to emit into that. So you get a very a strong decrease in the recombination lifetime, which means that you're emitting more light instead of the light recombining. Now, the reason why we only see a factor of 7 is because all of that light that you're emitting is basically being emitted into plasmonic modes. So what that means is it's effectively lost because there's nothing to scatter it to free space. So it's just propagating along and getting absorbed. But even so, just the cavity effect is enough to see a significant enhancement in emission. And remember, this is the exact same emitters, just a slight change in the substrate. We can also design electrically driven devices. So this is work led by a student, Andrew Briggs, here at UT. He's actually a student of Seth Banks, and we work closely with him on this project where he incorporated these dot emitters, these type 2 dots, into a LED structure. And again, we grew a control without the doping and a control with the high doping. That's essentially a quasi-plasmonic. This device is in fact not plasmonic. It's not the permittivity is not negative at the wavelength of emission, but regardless, you still get this cavity effect. And if you compare the undoped emission to, and this is electrically driven, to the doped emission, you see again this sort of dramatic enhancement. So not only can we do this with just a thin layer on one of our plasmonic surfaces, but we can integrate this into a PN junction device because, of course, our plasmonic material is nothing more than an N-doped semiconductor. So it's just the N++ part of a PN junction device. Now, the real opportunities in my mind here are for mid-infrared detector development. And the reason for this is if, you know, the type 2 superlattices are sort of the hot new material system for IR detectors, but there's a real problem with them, which is that you have a lot of benefits because you can essentially separate your electrons and holes, and that allows you to control the recombination energy or the absorption, the band edge essentially of this material. But by separating your electrons and holes, you've effectively decreased the optical dipole and you've made them less efficient absorbers, right? So if you look at bulk materials, what you see is a sort of very strong absorption, a very strong turn on of the absorption. So I'm plotting here, this is from a Rogalski paper. I'm plotting here the absorption coefficient as a function of photon energy. And you can see that for the type 2 superlattices, you're losing a significant amount of absorption. So they're not nearly as good absorbers. So what does that mean? Well, it's going to affect the quantum efficiency of your device, right? And so, well, you might say, well, who cares, right? I'll just make my device thicker. Maybe it doesn't absorb as well. I'll just make a thicker device. Well, there's a couple of problems with that. One is that the thicker you make your device, you still have to collect those electron hole pairs. So if you generate an electron hole pair deep into your device, it's unlikely that it'll end up being collected at the contacts or at the barrier of the device. So basically you have this, you're sort of losing as you go thicker and thicker and thicker. The marginal gains keep decreasing because your collection efficiency will go down. But the other reason is that your noise, or essentially your dark current, is essentially proportional to absorber thickness. So the thicker you make your device, then the more dark current you're going to have and the more noise you're going to have. And unfortunately, the way that we measure the quality of a detector is essentially two parts. In the numerator, we have the efficiency of collection, and in the denominator, we essentially have a noise term, right, or the noise equivalent power. That gives us the detectivity. So basically what you're doing is you can make it thicker. You're not adding anything to the numerator, but you're making the denominator much larger. So your figure of merit's going to go down. So how can we integrate our materials into detector devices? Well, the simplest way we could do it is, again, go and make a cavity-based device. So what I'm showing here are simulations. So this is the absorption for a long wave IR detector as a function of thickness and as a function of wavelength, just grown on an undoped substrate. You can see that absorption is very weak. It's in the sort of 10% range, even once you get up to 3 micron thick detectors. Now, if you were to put a metal film at the bottom of your detector, you would get essentially a double pass geometry, and you would be able to sort of bump this up to, you know, maybe 20% or so. But of course, to do that, you'd have to coat one side and you'd have to come in from the back side. We can, of course, grow our long wave IR absorber right on top of one of our designer metals. And what you actually see is that certainly at these sort of long wavelengths and very thin detectors, you get a significant enhancement compared to the other two. But even at moderate thicknesses, you can get a rather significant enhancement. And it ends up being a significant enhancement in integrated absorption as well. So we did exactly this, and you can model the fields. You'll see that in the doped, the structures with the doped virtual substrate, you get a very strong field enhancement. And you can see these sort of characteristic dips in reflection associated with the cavity modes. So this is experimental and simulated data. And if we look at our simulated and our measured response, you see sort of really nice improvement in external quantum efficiency. So these are the solid lines here are two different detectors with different thicknesses. So we're just essentially tuning the cavity thickness, that interference resonance. And then the sort of matching colors are with a lightly doped, so it doesn't have the dope substrate. So you see, factor of 4 improvement in your quantum efficiency for these devices. Now, these are still wavelength scale devices. So we've not gone nano. These are still wavelength scale devices, but that shows that basically we can integrate active devices with our doped semiconductor materials. Well, let's think about how we can actually go nano. Well, the way to go nano is that we actually need to use the surface plasmon modes. So what I'm showing here is an SEM and a reflection spectra of a detector that's fabricated that basically consists of a very, very thin NBN detector. So this is 500, basically half a micron thick detector, but the absorber region is only 300 nanometers thick. So this is the absorber. We have a barrier and a contact layer. So our absorber is only 300 nanometers thick. And on top of that, we have, or below that, we have our plasmonic surface, and above that, we have grating couplers. So this, we first proposed this in a paper, I guess 3 years ago now. But now we've grown the structures and we've characterized them, and this is what the mode looks like on resonance. You can see that we're coupling into a mode that is bound to the plasmonic detector interface. So you have a very, very strong confinement of your light. And if we look at the quantum efficiency, right, you can see this is the quantum efficiency for our fabricated detector. This is experimental data in solid, and this is the dash data is our COMSOL simulations. And this is the external quantum efficiency that you would get if you got rid of the coupling antennas, if you got rid of the plasmonic material. So we have a 16-fold improvement in our absorption efficiency, and we're absorbing close to 42% of, or above 42% of our light. Not even that, we're absorbing more than that. We are converting 42% of our light to a useful electrical signal in a detector that is lambda over 30. So it's 1/30th the thickness of the wavelength of our light. Right, and this has real applications for detector figure of merit. So if you look at the D star, which is the detectivity, which is the measure of a detector, we are in the 10 to the 10. So this is sort of state of the art D star at temperatures like 130K. So this is these detectors absolutely, they essentially are beating state of the art. They're beating what's available commercially. And the reason is because we can go very thin without sacrificing our external quantum efficiency, but we decrease the noise, the dark current associated with the detectors. And I should note that if we grew this material in just a traditional detector structure, it would take 7.5 microns of material in order to get this same external quantum efficiency. And that's assuming perfect collection, which is unlikely in this material system. So we can actually go nano with our devices. We can even do some even cooler things. We can make this is a device where we have our plasmonic layer is buried. It's a thin plasmonic layer, and we grow a detector above and a detector below our plasmonic layer. So we're leveraging a different type of plasmonic mode. These are called long-range surface plasmon polaritons, and you can see that we can get a mode that is either on the top interface or one that's on the bottom interface. And when we apply bias, we essentially shift between these two detectors, and effectively we can design a detector that controls the wavelength at which it absorbs simply by flipping the bias, whether we're collecting from the bottom or the top detector. So we fabricated this as well, and you can see these are just preliminary results, but you can see that in fact we do get a fairly nice switching depending on whether we're operating in reverse or forward bias. Finally, we can even forget about plasmonics altogether, and we can use the fact that we can engineer our dielectric. So in the mid-wave infrared, our N++ is a low index dielectric. So we can make a dielectric waveguide, and we can couple into that waveguide using a grating structure. This is all epitaxial. And this is the band structure here, and this is our dielectric, our refractive index as a function of position. And this is done, we basically confine the mode by using a heavily doped semiconductor on the bottom. And these are our simulations, but I just want to sort of show you the results here. When we look at the device that has the doped semiconductor, essentially that has this waveguide, we can get over 50% external quantum efficiency in this really nice narrow peak compared to our control, where we're only getting about 10% absorption, right? And so this is a guided mode resonance that we're leveraging here. And so we can tune that by controlling the grating and the angle of incidence and these sorts of things. And most importantly, we can do this in a detector absorber that's only 250 nanometers thick. So if you look at the comparison to the rule of 7, which is the rule for dark current that people use, that says that this is the state of the art that you could get for a commercial detector. We're below that, in some cases by an order of magnitude below that, and about 2 orders of magnitude below what you would typically get for a detector with that sort of efficiency in this material system. And again, D stars in the 10 to the 10 range, and this is at 200 Kelvin. So we're operating with what is a pretty hot temperature for an infrared detector. And I know I'm running out of time, so I'm just going to skip over this, but I do want to say that one of the things we've done recently is we've taken our hyperbolic metamaterials and we fabricated them into funnels. And it turns out that when you have a hyperbolic metamaterial, you've basically beaten the diffraction limit because of your anisotropic permittivity. You can confine a mode to ultra sub-wavelength dimensions. So what we have here is essentially a device where the funnel essentially takes a waveguide, a metal-clad waveguide, and brings it down to sub-diffraction limited thicknesses or areas. And we showed that we could actually get sort of strong transmission through even sort of single funnels. And so this basically, you can think of this as essentially a connection between the nanoscale and then the sort of micro or sort of wavelength scale, using this sort of adiabatically tapered hyperbolic metamaterial funnel. This was work done with Professor Victor Podolsky's group at UMass Lowell. And then most recently, we integrated some quantum dots into the top layer of this funnel. And we showed, in fact, that we can get an appreciable photoluminescence signal. This might not look that impressive, but you have to remember that we've basically etched away all of our dot material. So this is what you get just with the bare epi material. When you etch away everything except for that very tip of the funnel, you're still getting about only a factor of 10 or less decrease in your emission efficiency, but you've essentially killed the fill factor of your emitter by a factor of 400. So we're looking at ways that we can integrate sort of quantum emitters into these hyperbolic photonic funnels in order to sort of connect, ideally, single photon emitters at the nanoscale to the far field using these types of hyperbolic structures. So with that, I will end. I think I'm a little bit under. Well, I'm under an hour, so there's a little bit of time for questions. So I'll just say that the mid-infrared offers a unique spectral space to engineer the optical properties of materials, but also to engineer device architectures and optical transitions. And we can do this all in the 6.1 family of semiconductors. And we've leveraged this system to demonstrate enhanced efficiency emitters and detectors in the mid to long wave IR, but with nanoscale dimensions that are essentially state of the art, right? And so we've shown that we can couple light, long wavelength light, down to the nanoscale. And as we move forward, we're looking to develop sort of ultra thin, ultra small, sub-diffraction limited optoelectronic devices for the mid-IR with state-of-the-art performance compared to existing commercial devices. So with that, I will end, and thank you very much all for your attention.
That was fun. Thank you so much. I'm sure there'll be questions. If not, I have lots. I can keep going for a while. But let's see first if anyone wants to jump in. Well, folks are thinking, can you go back to the slides where you were showing your first change in photoluminescence? When you put the dope sample at the bottom, it's like a little bit more. Yeah, there we go. So I was wondering, and I know the answer will be different for all the different kinds of approaches you have shown, but how can you control the wavelengths now? What's the impact of dope? I mean, I know when you don't dope, it goes away more or less, but if you keep doping, will there be a limit? Will it still have an impact that's bigger on the wavelengths, or do you have any control about the wavelengths?
Right. So yeah, that's a really good question. So in terms of the wavelength so this is a balancing game, right? You have to tune your optical transition. Oh, I'm sorry. You have to tune your optical transition to essentially the optical environment that you've engineered with these materials. So there's three things that you have to play with. One is the quantum engineering of your emitter, right? And so we can control this now pretty well from 5 microns effective band gap out to 15 microns. So we can tune that however we want to, right? And the band gap essentially is, you can think of it essentially, you can think of the optical density of states roughly as being the square root of E dependence that you would get for a bulk semiconductor. It's a little bit different because, of course, it's a superlattice, but close enough. So you have control over your your cutoff energy, or your effective band edge. And then your doping controls the plasma wavelength. So essentially, you can control the doping to essentially take the Drude description of the permittivity and shift that in wavelength. So you could have your material have an epsilon near 0 response at the emission wavelength. You could have it be negative permittivity. You could even have it be sort of highly negative permittivity. And then the third thing in these structures is the total thickness of your undoped epi layer, because what that does is it controls the leaky cavity resonance, right? So it's a cavity effect, it's a materials effect, and it's an optical transition effect. All of those are tunable.
But in principle, I would have to change all of them at the same time if I wanted a new frequency. Correct? Like, do I have to make distinctly, let's say I want to have 2 distinct differently wavelengths for maximum absorption, I have to make 2 distinct differently setups.
So in this planar device, because it's just a planar, yes, I think that's largely true. That you could tune. So I think what would happen is if you tuned the emission off of the resonance, you would essentially weaken the enhancement, and you'd pull. I don't know if can you see my pointer?
Yeah.
Okay, you would essentially pull this out to longer wavelengths. I don't think you'd see as dramatic an effect. So to truly get the enhancement, to keep the enhancement and shift the wavelength, then yes, you would need to tune. You would need to tune all of those at the same time, though the doping probably not as much, because as you move to longer wavelengths, your doping just becomes more metal. It just becomes more like a cavity, traditional cavity. Now, if you put a pattern structure on the top, like our surface plasmon detectors, these ones, right? Now, in some ways, you have even more things to tune, because of course you have the band structure of your semiconductor, you have the geometry of the top grating, you have the doping of the underlying layer, et cetera, et cetera. But in some ways, tuning any one of them, you can shift things around. So you could probably tune this peak just by changing the geometry of your top antenna layer.
What would happen if you, so some of them used your ENZ, right? The ENZ crossing. What would happen if you could turn the ENZ behavior off with like a bias or something? And then I promise I will stop asking, and I will let someone else.
So that's a really good question. So we've looked into that, and I know that there's a number of groups who've been playing around with this. So for instance, Igal Brenner at Sandia, your old colleague, has been looking at very thin layers of ENZ material and trying to gate those and look at tuning. We tried a long time ago to tune dope semiconductors, and my sort of end feeling on that was that there's just a lot of carriers to slough around, and it's very difficult to do that in a 3.5. So we didn't have a lot of luck to sort of dynamically control that.
Yeah, I was just curious what would happen if you could in this case. Okay, thank you.
Well, I will say that in this geometry, there might be something that you can do. This is a very thin this is a very thin active region. So it is conceivable. We have been working. I should also note that I have a student who's been developing N++ P junctions where he injects carriers from the N++ material into the P-type material and tunes its optical properties. And we have a number of papers showing that you can sort of shift things around a little bit. The shift isn't as large as we would like, but in an SPP configuration, you might be able to get a dramatic effect.
Okay, cool. Thank you.
Thank you.
See. Any other questions? I know Gabe had a question, but I also see Jen and Miguel unmuted, so I'm thinking
I have a question.
just talk away.
Yeah.
I'll jump in real fast. Just going back to one of the slides Anas was asking about, where you have the photoluminescence enhancement on the plasmonic surface. What is the distance dependence? Is it still 1 to 10 wavelengths? And how does that fall off for that enhancement?
The distance dependence, meaning
how far away that plasmonic material can be from your photoluminescent material and still have as good of enhancement, and how does it fall off, basically?
That is such an excellent question. And in this geometry, I think the answer is probably doesn't fall off much. So we actually have simulations that show, and I wish I should have added them to that, but Victor did really nice simulations where he took a dipole and he moved it from the surface up through our emitting layer, which is about 300 nanometers thick. So he basically in his simulations, he took a dipole from essentially here and then just moved it up. And it turns out that actually your most efficient outcoupling to free space is away from the plasmonic interface. And the reason for that is exactly what I was saying. I sort of said it rather quickly, but you get this huge Purcell enhancement, but all of that emission is just going into your plasmonic modes, and it's basically all just lost, right? So in a perfectly planar structure, you actually probably don't gain a whole lot from the plasmonic effect. You probably gain more from the cavity effect. The reason why you can have a cavity effect in a very thin layer is because your permittivity is closer, right? Because you're essentially playing with the phase of the reflection at your plasmonic detector interface. And so when you do that, you can make a cavity that's ultra thin, because you can essentially play with that phase, and you can get the destructive interference that gives you the cavity effect. So that's why we can do these sort of ultra thin cavities. The emission enhancement is largely going to be a result of the cavity effect and less so of the plasmonic effect, right? But that's really an excellent question. And I should also note, there's one other thing I want to note, which is that if I was a pure optics person, then the answer to your question is, you want the emitter as close as possible to the plasmonic surface, because all optics people know that that's where your fields are the strongest. But in fact, as a semiconductor person, I know that if I take an emitter and I put it near a huge mess of carriers, I'm going to run into all sorts of problems in terms of non-radiative recombination that's unrelated to plasmonic effects, that is entirely related to semiconductor physics. And so there's a trade-off there that we're still thinking about, and it's not necessarily an easy thing to study. So
I saw Ryan has a question. I'm guessing it's a follow-up, so just go ahead.
Yeah, I just have a quick question. This Purcell enhancement is really fascinating. By the way, thank you so much for such a wonderful talk. That was fabulous. I was wondering if you could, maybe modify this planar structure. I was wondering how far you might be able to push this Purcell enhancement, instead of using, because if a planar structure will form an unstable cavity.
That's a really, yes. So the short answer is, we of course are limited by the real world, namely losses. And as much as I would love to be someone who doesn't have to worry about losses, it turns out that they're rather significant in any plasmonic material. Now we have a purely single crystalline, epitaxially grown plasmonic material, so I feel pretty confident that as things go, we have a good quality plasmonic material. That doesn't mean that there are no losses. That scattering term in the Drude model is a loss term, and that's going to kill you every time. So there is absolutely a limit. It's not as if we can make a Q of 2 million type cavity with the plasmonic material just because it's an epitaxial material. We're always going to be, our Qs for any sort of resonant structure in the mid-IR using a plasmonic material, I think we'd be lucky to get to 200, 300. I think that sort of level would be reasonable. In terms of the field confinement, I think it's, you can get a significant enhancement of your fields. The problem is always that you need to get the light out, right? So there's this balancing act between having this sort of very strong Purcell effect and then putting something into that system that outcouples the light. And that's the real balancing act. And then I guess the other thing I should note is we, of course, have thought about making plasmonic lasers because that would sort of seem to be a natural thing to do. But the simple fact of the matter is the losses you're going to have are just way too high. You just will not be able to get that type of gain in a semiconductor material. So I think a semiconductor laser is out of the question. But what's really, really cool, and the argument I always make, is that if you're someone who works in the near IR or visible, you have all of these amazing sources and detectors. I mean, you have such high efficiency lasers and such high efficiency detectors. And the problem with plasmonics, which has rightfully been panned over the last 10 years as not delivering on all of its promises, is that when you introduce metal into these amazing optoelectronic devices, it kills them. It kills the efficiency immediately, right? And you basically, you take your 90% efficient device and you transfer all of that energy into a mode that is at best, 30% efficient. You're just killing right? But the real advantage that we have in the mid-infrared is that we don't have any efficient emitters. We don't have any efficient detectors. So when we take a mid-IR sort of optical mode and we transfer it to a plasmonic mode, if that plasmonic mode is 30% efficient in terms of outcoupling to free space, that's a huge win because a mid-IR LED is 0.1% efficient. So if we can take a 0.1% efficient device, transfer that energy into plasmonic mode and outcouple 30% of that energy, that's a 300% improvement, right? And so that's where the real wins are in the mid-IR. I sort of didn't mention this, but the reason why we can do this is because the mid-IR is not have a lot of efficient devices. So we can actually gain with plasmonics instead of killing our device performance.
San Miguel, right? You had a question? You're muted.
Thank you very much for the talk. I really enjoyed it. I would like to ask you about medical applications, and let me talk what I mean. Right now, the way to detect breast cancer is mammography, which is X-rays, who for some women has a error of 50%, okay, because depending on the tissue. The other alternative is magnetic resonance, which is very, very expensive. And one technique that is being used is just infrared thermal images, in which you can see the tumor, but the problem is it's too big. I mean, the resolution is not good. So when you see the tumor, it's already too big. Do you see a way of application for medical images, this kind of technology? Can you see a way, a path?
So, I mean, the wavelengths that I work in are strongly absorbed by tissue and by water. So realistically, you can't penetrate more than a few microns into human tissue using sort of 10 micron light. Now I know that there are people working on near infrared imaging and cancer ablation technologies, and so I think that at shorter wavelengths you can dig deeper. I know that there are people who are working on skin cancer detection using infrared imaging. I don't want to say I'm skeptical. I don't know enough about the area. I have my concerns. A lot of the things that I've seen have been, they don't look, a lot of the people offering these services, I don't know how scientific they are. They're basically taking infrared thermal pictures of people's skin and then claiming they can detect cancerous lesions. I'm not. I don't have the sort of medical background, but in terms of actually three-dimensionally imaging, cancers or tumors, I think that's going to be hard at these wavelengths, but at shorter wavelengths, it might be possible. I know that's something people are interested in.
Thank you very much.
Thank you. There was a question about the temperatures. So the question is, whether this was done at 4K, 77K, or 300K. And thank you. I really did gloss over that, and I do apologize. So for the LEDs, these LEDs this is shown at room temperature. So it's not easy to get a mid-IR emitter at room temperature, but these emit rather nicely. In fact, you can see that over the course of going from essentially liquid nitrogen temperature to room temperature, our plasmonic LEDs, this plasmonic resonance or this sort of enhanced resonance doesn't actually decrease much. At best, it's maybe a factor of 2 we lose in this peak, but in the control device, we lose most of our emission. It's pretty noisy by the time you get to room temperature. So some of these devices do work at room temperature. The detectors, this work is at low temperatures, liquid nitrogen. Nothing is at helium temperature. I can't afford helium. And the plasmonic detectors, these are measured at 130K. 130K is actually pretty hot for a long wave IR detector. And we actually think that this was not designed for high temperature operation. We think that with a couple of tweaks to the design, so what basically happens is, as you go to higher temperature, these are narrow bandgap semiconductors, the bandgap decreases, it gets really, really small, and so your thermal noise goes through the roof. So if we design for higher temperature, it means we start with a wider bandgap, and as we get hotter, so at cold temperatures, it won't detect, but as we get hotter, the bandgap decreases, and then we sort of shift into this regime where our band gap is aligned to our optical resonance. And I think we should be able to get to sort of TEC temperatures for a long wave IR detector, which, by the way, would be a very nice result. And then the guided mode resonance detectors, these are operating at 200K. So that already is at a temperature where you could imagine TEC cooling perhaps. And these are really, really high response for a temperature that hot. In fact, these could be considered high operating temperature devices.
We should probably call it. I know there's gave us another question. We'll just stay on afterwards. If anyone else wants to bug then a little bit longer, feel free to stay on. But thank you so much. That was so fun. I loved your talk. It was very exciting work.
Oh, my pleasure. Thank you so much for
Awesome.
inviting me. It was a real pleasure, and thank you all for the wonderful questions. It's really nice to get questions that actually suggest people stayed awake during the talk. So that's awesome.
Awesome. Yeah, it was really fun.
Thanks, Dan.
So
Thank
we'll
you.
do-
Thank you.
Wonderful talk. Thank you.
Thank you.
Yeah, that was great, Dan. Thanks so much. That was just tremendous structures. Wonderful talk, but wow, I was just blown away by the structures you're creating there. Yeah,
Thank you
I
so
did have
much.
I did have a question about and it's similar to what Inez was asking, but a little bit different in terms of line width. And you've got all these incredible tools, and so on average it seems like that your half width maximum is maybe about a couple microns or so. And this is more just one of my, and these structures were phenomenal here when you see these narrow line widths. And one of the questions I had was, in your tool set, what do you have available to start playing with some of the line widths and the spectral characteristics, and what do you think you need to get to, especially in terms of when you're moving towards either detection or emitters? How refined do you have to be?
Yeah, it's a really good question.